Our next speaker is Terry Fong. Terry Fong is director of the Intelligent Robotic Group and senior scientist for autonomous systems at NASA Ames Research Center. Terry currently leads the NASA Human Exploration Telerobotics HET project, which develops and tests advanced telerobotic systems on the International Space Station. He is also deputy lead of NASA Resource Prospector mission Lunar Rover. From 2002 to 2004, Terry was deputy leader of the Virtual Reality and Active Interface Group at the Swiss Federation Institute of Technology. From 1997, wow, he's got a good resume, to 2000, he was vice president of development for the Fourth Planet Incorporation. He's published more than 100 papers in space field robotics, human robotic interaction, virtual reality, user interfaces, and planetary mapping. He received his BS and MS in aeronautics and astronomics from MIT, and his PhD from Carnegie Mellon. So his talk today is interactive exploration robotics, human robotic collaboration and interaction. And I'd like to introduce Terry.
Great. Thanks very much. Oh, wow, that is really loud. Good morning, everybody. It's a great pleasure to be here. I guess my role here is to be kind of a bridge or a segue or something between this morning, where we heard from Kip and Eileen talking about science and the use of high latency telerobotics on Mars, to ultimately what will be the discussion of later on this week, really a workshop focused on low latency. So I thought what I'd do today is tell you a bit about some of the work we've done at NASA Ames during the past decade, really focused on what I would call interactive exploration robots. We've sort of spanned the whole spectrum from low latency to, I guess, medium latency. But really our focus has been on trying to make exploration systems using robots in particular be highly interactive. Highly interactive for different kinds of tasks, supporting different kinds of science, including field science. And I'll take you through that whole spectrum. So to begin with, I want to remind you all of where we stand today in the state of the art of human planetary exploration. This, of course, is a picture from Apollo 17, Jack Schmitt and the Lunar roving vehicle. This was December 1972. So if you do the math, that's quite a bit of time ago. More than 40 years ago. And this is still the state of the art of how we know how to explore off of this planet. But a lot has changed since then. A lot of technology has been developed. We now can use satellites to acquire remote sensing information. We've learned how to use landers and rovers to explore planetary surfaces. We've even created spacecraft that crash into things like Alcross, or land on things like Rosetta. And we've started exploring how we can use humanoid robots in space. And I think there's a talk tomorrow that Julia Badger is going to be talking about focused on humanoids. So a lot has changed. And part of the question is, how do we use all this technology in a way that makes a lot of sense, that allows us to be more effective, more efficient, hopefully more productive in working in space. One of the areas that I think is really important to understand is that we've relied a lot on robotics during the past couple of decades to do this, especially because there are a lot of places where we just cannot go, at least not for extended periods of time, as humans. I want to point out, however, that there are many, many forms of human-robot teams. It's not simply the idea that a robot is a glorified screwdriver or hammer. It's not just robots or tools. I know a lot of people out there in the world tend to think of robots as tools. Oh, hey, this is my remotely operated joystick thing. But they can be a lot more than that. And in particular, there's a lot of interest, at least in the robotics field, of how we can provide these systems with more autonomy. Onboard basic competencies to function independent, at least for periods of time, from human operators or human controllers. There's also really, I think, a fascinating thing going on now to look at how we can have concurrent, independent, coordinated activity between humans and robots. The idea that you're not really fixated on the idea that you have to have continuous human in-the-loop control of robots, but really that we can create robotic systems that can function independently and coordinate, sync up, much like we all do. I mean, unless you're dealing with a toddler where you're doing continuous real-time control, most of the time when we interact with each other, we talk, we coordinate, we sync up from time to time. And I think that we'll see as we go forward that robots are very much the same way. However, to focus on the specific topic that I'm going to talk to you about for the next maybe 30, 35 minutes or so, There's been a lot of work that we've done at NASA Ames over the past 10, 15 years or so focused on interactive exploration in robots. And this is really, as I mentioned, really centered on the idea that robots can be controlled, they can be commanded, they can perform tasks in a fundamentally interactive manner. That it's not merely let's plan something, send it off, wait to the end of the day, we'll see what happened. And it's really, I think, a fascinating thing if you look at the different configurations that you can use to operate these robots. I'm going to take you through a series of things. Start off with part one, the idea of having humans on Earth and a robot in space. Not on another planetary surface, but just in space. Then we'll talk about the idea of humans on Earth and an interesting thing that NASA is working on right now, which is hopefully a near-term lunar rover mission. So much closer than Mars, shorter time delay, higher bandwidth. And the question is, how does that change the way we design the overall system? What are the things that are really fundamentally different between, say, lunar rover missions and Mars rover missions? A third part is something that's, I think, just gained a lot of interest over, say, the past 7 or 8 years, and this idea of having humans in some spacecraft in orbit, be that above Mars, an aerostationary orbit, or just in general being in some place where they have a robot on the surface, but the humans are not on the surface, and we're using the humans or the robots really as a proxy for having boots on the ground. And the fourth part, I'm actually going to use a segue, because I know that Dan Lester is talking after me, to talk a little bit what I would call real-time telerobotics. And it's interesting to me that a lot of the work we did at NASA Ames in that area was work we did about 20 years ago. So, once again, not that we've necessarily reinvented the wheel, but this whole idea of real-time interaction, real-time telepresence has come kind of full circle again. And I want to leave you at the end of that with a little bit of what we learned back then. So we'll start off with part one, humans on Earth, robot in space. And I'll tell you that a lot of the things that we within NASA care about in terms of humans in space, or at least dealing with spacecraft, has to do with maintenance. You might think, oh, it's all just fun and glory and games and everything being in space on the space station. But the reality is most of the time is spent taking care of things. Most of the time is spent keeping the space station safe. Most of the time is spent maintaining things, whether it's preventive maintenance so that you don't have to worry about something breaking, or corrective maintenance when something has broken and you need to go fix that. There's a lot of work that NASA worries about on human spacecraft. And this is going to be true whether this is the space station today or some future deep space spacecraft over Mars or any place else. And that is, there's a lot of extravehicular activity, things that you have to do outside, things that are very risky and may take significant amounts of planning and preparation before you're willing to send humans out there to go fix things. But also in terms of intervehicular activity, there are a lot of things just inside of a spacecraft that you have to take care of. Because if you want to live inside of a closed can, you really need to make sure that that can will support you, that you depend on the fact that the environment is safe, that the air is breathable, that you understand what the other factors in the environment are in terms of sound, in terms of lighting, in terms of anything else that you have to worry about because you're going to be living in that space. Of course, on the space station, we use a variety of robots. Many of you are probably quite familiar with the Space Station Remote Manipulator System or the Canadarm2 system. On the end of that, there's a thing called the Special Purpose Dexterous Manipulator. I love these acronyms. I mean, who else would come up with these acronyms other than space geeks? Better known as Dexter. Inside the space station, of course, we currently have Robonaut 2, which has been up there for a few years. Spheres, which has just celebrated its 10th anniversary on space station. And a new robot that my group is developing called Astrobee, which will be up there in about a year. These are all IVA robots. And what's interesting about these robots is because we are dealing with a spacecraft, the space station, that's in low Earth orbit, we can interactively command and control, we can interactively monitor and look at the data that comes from these systems. The round trip latency is perhaps only a second by way of the TDRS system, and we have very high bandwidth, especially on the downlink portion, to get lots of information off of these systems. Just to give you an idea of the things you can do inside a space station, these are the spheres. This is actually sped up by 5 times. They're actually pretty slow systems. Just giving you an idea of robots we've had on space station, as I said, for 10 years. These were originally developed by MIT, jointly supported by DARPA and NASA, and they've been used actually very extensively. I think more than 120 crew sessions to date. It's by far the most used test bed on the space station. at least for microsatellite simulation and zero-G robotics work. A couple of years ago, actually not a couple of years ago, I mean it's more like 5 years ago, my group started working with them, and rather than treat these as small microsatellites, we said, let's turn these into robots. We did something kind of crazy at the time, which was to put a smartphone onto one of these as sort of a brain upgrade and also high bandwidth data link. And we looked at experiments that focused on how you could use a remotely operated robot, an interactively controlled robot, under control for mission control. We took a look at what sort of networking was required to do that. And you would think the space station would have a lot of facility for this, and you'd be right. There's a lot of networking on board the space station, wireless LANs, wired LANs. We have a nice communication infrastructure that makes use of the TDRS system to relay data to and from the ground. And of course, at JSC and Mission Control, very high bandwidth wired network. And so we looked at how we could use this entire system here to allow us to enable real-time interactive robots. This is an example of one of the tests that we did. This was back in 2012. Here is the Spheres robot flying around inside the Kibo laboratory. It's actually flying a lawnmower pattern. It's an imaging survey looking at this bulkhead wall here. It's flying back and forth. The crew here is only observing. The actual person who's dealing with this in an interactive manner is on the ground at mission control. And what that person is seeing, you'll see in just a minute here, is an interface that gives you information in real time about what's going on with the robot. So we're seeing live video feeds here. We're having real-time telemetry that we use to feed this 3D display. And you can see in real time, what is the trajectory, the traverse, if you want to think of it that way, the robot's flying. You also have information showing, what's it looking at. This is the projected field of view of the camera system. And the person on the ground who's doing the control here is really dealing with all this information in real time, just monitoring what's going on with the robot, trying to understand when there's new information being downlinked, is that important information that needs to be dealt with immediately? Does the robot have a problem? And if it has a problem, do I need to switch to a different control mode? The interesting thing about this is the robot is fundamentally autonomous here. We're interactively monitoring it. We're watching what's going on, but we're letting the robot do most of the work. It's figuring out how to fly from waypoint to waypoint. It's making decisions of when to stop, when to acquire new data. There are places, for example, on this survey where it will stop and take panoramas. But the idea here is that the human is really not directly in control. He's really supervising a fundamentally autonomous system, but in real time. That's one way of thinking about the whole idea of how you can interact with a robot, very interactively. Another way is thinking of how we could do this if we're looking at places that are closer than Mars. Eileen did a very nice job talking about how we use high latency telerobotics for doing Mars rover operations. A lot of that is driven by the kinds of science that's being done on Mars and the systems, obviously. And it is true also that a lot of it is driven by the tremendous distance we have between Earth and Mars, and therefore the associated limitations on latency and bandwidth. However, there's another large target of interest to at least some portion of the planetary science community, and that's the moon. NASA right now is working on developing a mission that will be launched in the 2021-2022 timeframe called Resource Prospector. If you're not familiar with Resource Prospector, this is a mission that's designed fundamentally to be a real-time subsurface prospecting mission. We're looking for subsurface water ice, or at least subsurface species of hydrogen. And we're doing that with a couple different prospecting instruments, a neutron spectrometer and a near-IR spectrometer. But in addition to that, there's subsurface access device. There's a drill, relatively short drill, only down to, I think, 0.5 meter to 1 meter depth. And then a variety of instruments that will take any of the samples that are collected from the surface, heat those up in a controlled manner, and look for the evolved volatiles. This is a mission that really is a bit different in many, well, not just a bit different, I would say fundamentally different in many respects. One is the science here is quite different than what we've used rovers for in the past 20 years. Here, the focus is not field geology. The focus here is looking for volatiles. We're looking for subsurface materials. We're looking for evidence that we can make use of these materials for future space missions. We're really trying to look for things that you can't just see with the naked eye. In fact, you can only see these things through readings we get from instrumentation. Another thing is that we are using direct-to-Earth communications. So if we send a robot, be it to the South Pole or to the North Pole here, we are going to be constrained in a few different important ways. One has to do with the fact that we are using direct-to-Earth communications, and it's low angle to the horizon, which means we have to be very cautious about how we deal with the operations. If we move into a place where we block out the Earth and we lose comm, and that makes it really difficult to run a mission like this. There are other concerns that are quite different from Mars as well, having to do with the environment here. For example, at the lunar poles here, we're going to be operating in places with also low angles of illumination, which makes it very, very difficult to image from orbit. It makes it also very difficult to operate on the surface here. And the last thing I think is really important to take away from this here is that the rover that we're looking at here is going to move in some sense at light speed compared to what our experience is on Mars. We're looking at speeds of around 10 centimeters per second, continuous. So this robot is moving very, very quickly, okay? For anybody familiar with MER, MSL, I mean, the idea that you would have a robot operate this fast over unknown terrain, probably sends shivers through your spine. But it's something that's important for us because we're trying to carry out this mission with a solar-powered rover within 1 lunar day, which means that we have 6 to say 10, 12 days of real actual operation time. So it's a very short period of time to try to accomplish a lot. This is an animation of what we think the mission might look like. So here we have a 4-wheel, 300-kilogram rover carrying instrument payload that, as I said earlier, involves a neutron spectrometer and a near-IR spectrometer. Fundamentally starting off with a prospecting activity. So here our science is really traverse-focused in terms of collecting data across the entire path that you're moving. You may end up doing area of interest mapping, so you may go to certain areas and try to find hotspots, look for gradients of the materials that are in the subsurface. You'll have to go to places where the illumination is very, very difficult, or that will only be provided by illumination carried by the rover. And of course, you start getting into all kinds of interesting effects here too. The fact that if you are carrying lights and are pointing forward and your cameras are aligned with the lighting, you're going to have to deal with things such as the opposition surge effect with lunar regolith. And even after all of that, if you're able to successfully maneuver the robot around, then you're going to have to figure out, well, how do I get to the really interesting places in these dark, permanently shadowed regions where we're looking for cold-trapped volatiles. So the interesting thing about this, as we wrap all that together, is really how different fundamentally this is from Mars rover operations. In terms of the science, in terms of the robot interactivity, in terms of the communication, in terms of the instrumentation, all fundamentally different from what we've experienced to date on Mars. To try to explore how this would really work in real time, especially in terms of science operations, we've done a bit of testing. Back in 2014, we did a 2-week field test on the Mojave Desert using a rover that wasn't quite the one that we're going to be using for Resource Prospector, but which was used as a proxy to try to examine some of these real-time prospecting scenarios. We looked at real-time operations with a science team at NASA Ames, and here's a better picture of the robot we're working on, carrying, as I said, a couple different instruments, the near-IR spectrometer and the neutron spectrometer. This is the science operations room at NASA Ames. And what's interesting here, too, is that we've really tried to go a bit further than what we currently use today for Mars operations. A lot of these tools here are web-based, designed to be very lightweight for deployment, something that somebody can walk in with a laptop, turn on, and immediately be fully immersed in operations. Give you an idea of some of the things we're doing here. And again, this is meant to represent the kind of robot activity we're going to be carrying out when we get to the moon. This is the K-Rex rover from my group at NASA Ames. Underneath that black blanket is the near-IR spectrometer. On the back, right here, is Rick Elphick's neutron spectrometer system. Here on Earth, of course, we carry our own radioactive source for interrogating the subsurface. That's a little californium-252 source. And this is the kind of terrain that we're operating in the Mojave. The interesting thing here, I think really for this particular workshop here is, as I mentioned, it's fundamentally interactive. We're trying to really push the boundaries of what's possible in terms of interactive science operations. We're looking at planning and commanding in real time. We're looking at monitoring in real time instrument data. And it's a lot to take in. It's also driven by the fact that this robot is moving a lot faster than many people on our science team are used to. The idea that you're trying to do real-time analysis of data coming off of a rover moving at 10 centimeters per second is very, very challenging. And of course, the big question is, are we getting the right data so that later on we'll be able to go back and when we have time to really analyze it in detail, make sure that we really understand the site. Another thing that's, I think, supporting this here has to do with the fact that we're trying to use different kinds of operation tools that have been used from Mars. Part of this has to do with looking at tools that are very, very interactive. I'll skip past the first one, which is really focused for robot operations, and a system we called XGDS, which allows us to really collect and interrogate data sets in real time. And when I say real time, of course, real time is very relative. This is certainly real time in terms of the way this rover operates compared to Mars. It's certainly not real time in terms of looking at 1,000 hertz kinds of data. But what's interesting too is that the robot here is moving about 10 centimeters per second. It's sending lots of instrument data that we may end up plotting in real time, looking for particular signatures or places where the signal indicates maybe we should spend more time and we should go back and do an area of interest mapping. And it's a lot of information to take in, a lot of information. If you see all these tabs here that are kind of hidden behind this strip chart right now, lots and lots of data for the site that we gain over time. So part of the question when you're looking at systems like this is really how do you manage this vast flood of information, this really sort of fire hose of information. Part of it is I think, addressed by the structure of the science team. Part of it is fundamentally about the kind of science you're trying to carry out. Part of it really has to do with just how do you have tools that allow you to really deal with the complexity of lots of information. That's something that I think going forward is really important. It's not just about how fast can you get the data down. It's really how do you deal with the data that you're getting. Moving on to the third area, looking at the idea of humans in space and robots on the ground. As I mentioned earlier, there's been a lot of interest the past few years of this whole notion of, oh, hey, maybe we don't need to actually send people to the surface. We can just send a robot there. The robot is something that can last a long period of time. It can get dirty. Maybe it saves us from having to build a human-rated lander. We can have a robot-rated lander. And it's kind of interesting to me as a roboticist that we're willing to send robots to the surface and not humans, and that's a whole different story. And so one of the things that we started looking at a few years ago at NASA Ames was, if we are going to carry out these kinds of missions, what's really involved in building them? What are the key factors in terms of the actual numbers you need for bandwidth and latency? What are the key things you have to go through in terms of what's required by crew for training, for experience? What sort of displays will astronauts need to be able to carry out these kinds of missions? So one mission that we chose to use as a reference mission is a mission called Fastnet. This is a concept of sending a human spacecraft, such as Orion, to orbit the moon, perhaps at a distant retrograde orbit. And from the spacecraft here, you would have astronauts remotely operate robots on the surface of the moon, carrying out a variety of tasks. They could be performing field geology, they could be deploying a radio telescope, they could be collecting samples, a variety of things. But the idea here is have people close, have the bandwidth, high bandwidth, have the latency short, and look at the way you could do future surface operations. To study this, we created a series of tests that involved using the space station as our proxy for our future spacecraft. We set up a series of tests during 2013 that involved 3 different crew from ISS Expedition 36, Chris Cassidy, Luca Parmitano, and Karen Nyberg. And we tried to implement in an analog manner this mission, which was really focused first and foremost on the surveying and then deploying and then inspecting a lunar radio telescope. And we would use the robot with the crew to carry out all these different mission phases. Because we're using the space station, of course, we're in some sense constrained by the communication architecture that's available at the space station. You can see that here we have, on the downlink side, about 500 millisecond delay. On the uplink side, similar thing. We try to transmit lots of information from the rover up to the space station, which means we're constrained by what TDRS can provide. In this case here is about 800 kilobit per second on the uplink. But commanding the robot here, because there's really only sending position commands or at least waypoints, very low bandwidth. We used interfaces like this. This ran on the space station computer on board the ISS. This is the interface that the 3 astronauts we worked with used with very little training. They had basically half an hour training to prepare for each of the different phases and then operated the robot accordingly. This is providing a supervisory control mode. You can see they'll load up different plans to be executed by the robot and then interactively watch what's going on with the robot. Lots of detailed information here representing 3D terrain hazards, providing different views of the robot, live camera images, and really up to them to decide when they would need to intervene and interactively take control of the robot to help the robot get past, for example, hazards. Just give you an idea of what this test looked like. This is an outdoor test area at NASA Ames called the Roverscape, which we set up for this mission simulation here. This is one of our older robots called K10. This work was really done very closely with Jack Burns. Many of you probably know him, University of Colorado. Jack's one of the people that's behind the whole Fastnet mission concept. Here we had a planetary rover equipped with a number of imagers, as well as other sensors just for robotic operation, and a variety of terrains that had to deal with, positive obstacles, these rocks and slopes. There are a couple of craters as negative obstacles as well. What's interesting, I think, is looking at the kinds of tools used by astronauts. So this is Luca Parmitano. This was during our second session. You'll notice he's watching this robot in real time. He's getting live updates of the obstacles detected by the robot. The robot's using a variety of sensors. It's using stereo vision and a 3D laser scanner to provide information about the terrain. It's turning that into its assessment of what's safe and unsafe. The red areas are what it deems to be unsafe. And it's doing this in real time by computing metrics such as step obstacle size, roughness, cross and side slope information, and then feeding that all to this display for the operator, in this case an astronaut, to deal with. What's interesting here also is if you look at this here, he's having to understand in real time what's going on. He's using this 3D map. He's using camera images to try to build good situation awareness of what's going on with the robot. And he's dealing with it in real time, really interactively. It's something that I think is certainly a very different mode of operation than anything we've really done before. And because we're trying to do this from space, we were really constrained to operate inside the bounds of what's possible with the human spacecraft. If you're interested in the results of this, I point you to a nice paper that my deputy Maria Bolet wrote, published in 2012, I think, or sorry, 2014, that took a look at a lot of hard engineering data. We're trying to quantitatively assess what's possible with this system in terms of a variety of metrics focused on mission success, the amount of time you were using the robot, keeping it busy, the success at performing tasks, how the operators and the astronauts were able to deal with contingencies, especially the mean time required to intervene, all that kind of really good hard engineering things. And I think the big takeaway from here is that at the end of the day, it really depends upon the kind of surface activities you're trying to accomplish, and not purely on one single factor. Latency, and that we're going to talk about, I think, for the rest of this week, is an important factor, but it's not the factor. In fact, it's not the only factor. There are many, many factors. And sometimes minimizing latency is important, but there are many, many times when who cares about latency? Because what's really important may require other things. I want to just wrap up here with some old work. As I said, that it's interesting to me how we can come full circle, actually time and time again, with some things that we did at NASA Ames about 20 years ago. And that's really focused on this idea of real-time exploration telerobotics. How can you interactively, with very low latency, control robots and in some sense be virtually present? One of the things we did back in, I dug this up just over the weekend. I couldn't believe how long ago it's been. This was back in 1993. We built a system at that time called the Telepresence remotely operated vehicle. It was this Phantom ROV equipped with a small sampling arm and a pair of stereo cameras on a pan-tilt system here. And we remotely operated it from NASA Ames while this was deployed in McMurdo Sound in the Antarctic with a system like this, where you have a head-mounted display, you're looking at live satellite-fed video, you're controlling the robot in a variety of control modes, one of which is real-time manual control with a joystick. And this head-mounted display is not only showing you stereo, but it's a head track thing, and as you move your head, it changes the position of the pan-tilt unit. So real-time interactive presence with this system. This is some video that I digitized off of old videotape. I'm almost ashamed to say I still have a VCR, but here you can see the Telepresence ROV underneath the sea ice in McMurdo Sound. This is what's coming off a stereo imaging system at that time, coming back to Ames. Some of you may know Butler Hine, who was the Laddie project manager. Butler actually used to run the robotics group before me. He's actually my first boss. And here he's looking at some of the benthic ecology that we see in the sub-sea at McMurdo Sound. And here he's panning the Telepresence ROV imaging system around by turning his head. We can see on the screen the way that the system responds. And it's interesting that this is stuff that we did back in the early 90s. And we're here to talk about this stuff again today. Another experiment we did a couple of years later involved this rover. Some of you may recognize this as the Marsokhod. We took the Marsokhod to Kilauea, and we did a very similar sort of thing. We had a science team at NASA Ames remotely operate this system in real time. We fed live stereo imagery from this rover as it was doing field work back to the science team. And here, instead of just using head-mounted displays, we had shutter glasses and stereo monitors to allow the science team to have an interactive pseudo 3D view of what's going on with the robot. This is the Marsokhod at Kilauea. It's actually the southwestern desert area. For those of you familiar with Kilauea, this robot was equipped with a sampling arm that we used to acquire some samples. Just give you an idea of the kinds of terrain that we operated the robot in. Now, what's interesting here is that we conducted an experiment trying to operate this robot in what at the time we termed to be Mars mode, another lunar mode, where the fundamental difference really had to do with whether we were taking a strategy, kind of like what Eileen said, in terms of downlinking data and then spending a lot of time going through performing analysis and strategic and tactical planning versus lunar mode, where it was continuous real-time operations. Some of the things that we learned, of course, is that real-time continuous operations is highly, highly stressful to the science team and the science operations team. And there were a lot of questions that this study raised at that time about the real benefits of trying to do things really fast. When is that really appropriate? When is that helpful? And when is it not? So to wrap up, my last slide here is just a few lessons from this work that we did, as I said, more than 20-some years ago today. The first is in the area of latency. I said earlier that latency is only one factor, especially for remote telerobotics. And I think that as you look at the whole problem of what's really important, you look at other variables, the type of science you're trying to perform, the type of activity you're trying to perform, the instruments and the amount of data coming from those instruments directly constrains operations. The cost of these different missions, and that is not only in terms of the equipment itself, but the science team that's associated with that. The risk profile that you're going to associate with any of these missions. Eileen didn't talk about this on Mars, but there are real reasons why we take a lot of time to carefully validate the command sequences we send to Mars. We do not want to lose these robots. We can't just go out and fix them. We can't go easily replace them. Well, unless somebody's got a lot of $1 billion stashed someplace that I don't know about within NASA. A lot of other factors. Latency is only one factor, and I hope we talk about that this week. Another thing, too, is that remote robotic exploration is not dominated only by control latency. There are many, many, many other factors. Data collection, how long do instruments take to acquire data? How long does it take to transmit that data? How long does it take to analyze that data? How long does it take to make decisions? All of these things are, in fact, far more significant in time than just the latency for control purposes. That's something that's really important. Another thing that we found out had to do with the use of spatial displays. 3D visualization is really essential for a lot of field studies. I think most of the people here do field studies where it's essential to be able to visualize information in 3D space. Head-mounted displays and stereo video can help with that, but I want to point out that those are not true 3D displays. They're pseudo 3D displays. And that can lead to a lot of different issues, especially having to do with errors due to accommodation. You look at a shutter screen showing you stereo video, that is not the same as going outside and looking with your eyes at a natural scene. It was interesting to us also that even with the rudimentary graphics that we use, both in terms of pure virtual environments and then augmented reality displays where we'd overlay the graphics onto, say, video, that it didn't really require a tremendous amount of data to provide a true sense of presence. However you define sense of presence. I don't think that it's necessary to end up with the highest resolution in time and space data. What's more important is having the key salient pieces of information. That's what people care about when they want to be immersed in data. And then finally, in terms of real-time telerobotics, I do want to point out that the telepresence, and at least in terms of our experience, by itself is not a panacea. It doesn't solve everything. There are many, many, many other factors to consider. There are many other important things to think about as you're building and operating these systems. One of the things has to do with the whole focus on control of a system. Manual control of a robot, be it a rover, be it an arm, be it a free flyer, is highly imprecise. And it's highly coupled to human performance in terms of skill, experience, training, fatigue, everything along those lines. One of the reasons why NASA over the past 2 decades has tried to create more and more autonomy on board our systems is to reduce things that are coupled to human performance, human hands on joystick. And then lastly, as I mentioned earlier, minimizing risk, at least for a lot of these planetary missions, is far, far more important than optimizing operational efficiency. You don't want to lose the system. You don't want to lose an instrument. And if that is the dominating factor, I don't care how fast your system can run. I don't care how efficient your operating process is. This is what NASA cares about. And with that, I'll stop talking at you and maybe engage in some discussion.